For today's little mini lesson, we're going to look at factoring what's called GCFs, or otherwise known as greatest common factors. So today we're going to learn how to find the greatest common factors between a set of numbers, but also for polynomials as well. So the key vocabulary word is GCF, which represents greatest common factor. So let's begin. So first off, sort of the definition of a greatest common factor is if you have factors that are shared by two or more whole numbers, they're called factors. This is also true for variables. The largest of the common factors is what we call the greatest common factor. So if you look at the couple examples below, we have two numbers, 24 and 36. And if I were to define the greatest common factor between those two numbers, one technique is you could actually list all the factors out. So if you list all the factors of 24, 1, 2, 3, 4, 6, 8, and 12, and 24, and then same with 36 down below, comparing those two factor lists, you're seeing what is, number one, the number that's most in common with both of those, and number two, it's got to be the biggest one too. So notice we do have basically 1 through 6 is all same kind of factors there of 24 and 36. But the biggest ones that they share is going to be 12. And so we'd say our greatest common factor between 24 and 36 would be 12. So that's one technique, is when you're finding the greatest common factors, is just to list all the factors out. Another technique you could do is, if we look at 24, you could write out the prime factorization of 24. That's like what if we did our factor trees when we simplified radicals. So that was 2 times 12, that's 2 times 6, that's 2 times 3. And so 24 can be written as 2 times 2 times 2 times 3. And 36 can be written as, well, if I make a factor tree of that, that's 2 times 18, that's 2 times 9, and that's 3 times 3. So that can be written as 2 times 2 times 3 times 3. And between the two lists here, you circle all the same kind of factors here. So we have a 2 in each. In fact, we have 2 2's that I can circle. Those are in common. And notice we have 1 3 in the first one and 2 3's in the second one. So what they share is just sort of the 1 3. So together, 2 times 2 times 3 would be the factors that they share, the prime numbers that they share. And notice that also equivalates to a product of 12 too. So either way, doesn't really matter how you find the GCF, if you want to list all the factors of that number, or if you want to list the prime factorization of it, sort of expand that number, we call it. Either way, you're going to get to the right answer of that GCF. So let's take a look at a couple examples together, and then I'm going to have you guys try a couple before we swing over to some polynomials here with variables in the mix. So again, doesn't matter what technique you use. We could list all the factors of 28. So if I list all the factors of 28, well, 1 is a factor, 2 is a factor. It's not divisible by 3, it's divisible by 4. Not divisible by 5, not divisible by 6. It is divisible by 7. Basically 7 through, I think, 13 it's not divisible by, but then the next one up would be 14, and then 28. And if I list all the factors of 42, for sure it's divisible by 1. Also 2. It is divisible by 3 if you check. 4 is not divisible by 5. 6 is, because I know 6 times 7 is 42. And then it looks like I think 3 times 14 would be 42, 21, and then 42. So these would be all the factors of 42. And then now if I look at my big giant list, the biggest factor that they share in common is going to be 14. So then 14 would be considered our GCF, greatest common factor. And again, another technique is you could just write out the prime factorization, do a factor tree of 28. If you do a factor tree of 28, you're going to find out it's 2 times 2 times 7, the prime numbers in that. And then if you do a prime factorization of 42, that ends up being 2 times 3 times 7, if you were to work that out. And so if you look at the prime numbers, even the ones they share in common are the 2 2's and then the 1 2 and 1 7 that they share. And if you multiply those two together, you get 14 as well. So either way, if you want to list the factors or list the prime factorization, does not matter. So if we take a look at the next one, we got 3 numbers to work with. Let's maybe choose the factor route. I know 1 is a factor, 2 is a factor, it's divisible by 3. It's divisible by 6, it's divisible by 9, and then 18. If I list all the factors of 30, that's 1, 2, 3. It's not divisible by 4, but it is divisible by 5 and 6. Not 7, not 8, not 9, but it is divisible by 10. Also 15 and 30. And if I list all the factors of 24, that's 1, 2, 3, 4, 6. I know that 8 times 3, and then looks like 12 and 24. So if I look at my big list here, it looks like the biggest number that they share in common is going to be 6. So it looks like 6 would be, in this case, our GCF. So see if you can try these two. You can pause the video and try both of these on your own and see if you get the correct answer of what the GCF is. Good luck. So I'm just going to try for the first one, I'm going to try that prime factorization technique, because remember you can use either one. So if I were to write the prime factorization of 18, basically if I break down 18, that's 2 times 9, that's 3 times 3. And the prime numbers there are 2 and 3. So that becomes 2 times 3 times 3 as a product of prime numbers. And then the number 36, if I write that down, break that one down, that's 2 times 18, that's 2 times 9, that's 3 times 3. And so the prime factorization there would be 2 times 2 times 3 times 3. And so if I look at the two lists, what they share in common are for sure 1, 2 they share, and then also 1, 3. And so together that would be 2 times 3, which ends up being 6 would be your GCF there. Let's look at the other technique for the last one here. So if I list all the factors of 40, I know it's divisible by 1, 2, not divisible by 3, it's divisible by 4, not 6, or not 5. Actually 5 it is, not 6 and 7, but 8 times 5 is 40. Not divisible by 9, divisible by 10, not 11, 12, 13, 14. I think the next one up is actually going to be 20 then. So there's all your factors of 40, and then all the factors of 16 would just simply be 1, 2, 4, 8, and 16. And then the factors of 24, if you list those out, 1, 2, 3, 4, 6, 8, 12, and 24. And so if I look at my two lists and compare them, the greatest number that they have in common looks like to be 8. And so our GCF here would be 8. All right, so now let's apply this to some polynomials, which is our big focus today, because factoring is what we're going to be spending a few days on in this class and gearing up towards solving quadratics by factoring eventually. But before we get to that, let's look at a couple. We have some expressions now in the mix. These are considered polynomials, where you have some exponents and some variables in the mix. So when we're doing these ones, the best strategy is sort of break down each term separately. I like to use an expanding technique. And so what that means is I want to look at the prime factorization of 12, and then I also want to expand as much as possible x cubed. And so what that first term is going to look like if I do prime factorization of 12, that's 2 times 2 times 3, and x is x times x times x. And then if we look at 52 and do a prime factorization of 52, well, if I break down 52, that's 2 times 26, that's 2 times 13, and I think that's it for 52. So that becomes 2 times 2 times 13, and then x squared is x times x. And then basically look at the two terms and see what numbers and variables they share. Notice I have 2 2's over here, I have 2 2's over here. And also in the first term, I have a couple x's that I share with the other term. After that, that's just extra numbers and extra variables in each term. So what I'm left with in parentheses, we're going to leave what I didn't box inside the parentheses. So I didn't leave that 3 in that first term and that x. I didn't box the plus sign, so make sure you include that in your parentheses. And then I also didn't box the 13 in the other term. And what you're left with on the outside is whatever's boxed, we put that on the outside. So if there's 2 2's I can pull out, then that would be a 4 in front. And if there's two x's that I can pull out of each of those, then that would become x squared in front. So then this would be your final answer. A good way to check is you could always distribute that 4x squared through to each term and see if it equals that original amount. If it doesn't, then you might have made a slight mistake, so you can check your work that way. So let's take a look at the next one here. In the next one, this is a -9, so I guess if I break that down, prime factorization, I think the only way I can break that up is just 3 times 3, but there's a negative in front. And then n cubed can be written as 3n's, still have the plus sign. If I break down 18, that's 2 times 3 times 3, right? 2 times 9, and n squared is n times n. Still have the minus sign, and now if I break down 63, and let's do a prime factorization of 63 now. So 63 I think can be broken up as 3 times, I think 21, and then 21 is 3 times 7. So 63 itself can be written as 3 times 7, and then there's that extra n there. So if we look at each term separately, there's 3 terms here, and compare those 3 terms, let's circle the things that are in common with each of those. So it looks like there's a couple 3's in each of them. In fact, there's 2 3's here, there's 2 3's here, there's 2 3 here. And then looking at the n's, since that third term only has 1, then that means I only can share 1 between each of these. After that, the other terms have some extra n's that the other term doesn't. So it looks like I can pull out a 2 3's and an n. So what's going to go out in front of my equation would be, well, 2 3's would be 9, and an n would just be n out in front. And then what you're left with in the parentheses is what you didn't circle. I didn't circle the negative. I didn't circle those 2 n's, making it n squared in the first term. I didn't circle the plus sign or the 2 n's in the next term, or the 2 and the n, I should say, in the next term. And then the last term, I didn't circle the minus and the 7. So this would be our final answer. And again, if you're unsure, you can always distribute that through to see if it equals the original expression. All right, so I want you guys to try some on your own here. So you can pause the video and try both of these on your own. Notice the letter B has a couple variables in the mix, but don't worry, just expand that x cubed, that y squared, and see what they share between them. And we'll go over these here in a little bit. Good luck. All right, so in the first one, if I were to expand 6 can be broken up as 2 times 3, and then y to the 4th would be 4y's. 42, if I make a factor tree of 42, that's 2 times 21, that's 2 times 7. So 42 can be written as, that's 3 times 7. So that'd be written as 2 times 3 times 7, and then y squared can be just written as 2y's. So now if I look between the 2 terms and circle what I share, looks like I share a 2 and a 3, and I also share 2y's. And so if I pull out a 2 and a 3 in front, that's going to become 6, and if I pull out 2y's in front, that becomes y squared. And what you're left with in parentheses now is what I didn't circle or box. So it looks like the 2y's become in y squared in that first term. I didn't circle the plus sign, and I didn't circle that 7. So this would be our final answer in letter A. In letter B, if I break each term down, 4 can be written as 2 times 2. X cubed is 3x's. Y squared would be 2y's. Plus, if I break down 10, that's 2 times 5 as a prime factorization. And really, there's nothing I can do with the xy, so let's just write it as xy. And then the last term, 24, can be written as 2 times 3, I believe, if you do that factor tree. X squared can be 2x's, and then y cubed is 3y's. So if I look at between each term, for sure 1, 2, I can factor out because that's in common with each of these. If I look at the x's, since the middle term only has 1, I can only pull out 1x from these other 2 terms, so I share 1x with each other. And then looking at the y's, since the middle term also only has 1y, then that means the other 2 I can only pull out 1 of those as well. So if you look between each term, it's kind of hard to decipher with my circles here, but right, each term here. Then looking at each term, it looks like I can pull out a 2x and a y. So what's going to be in front is just simply 2x and a y, and what I'm left with in parentheses is I didn't circle the 2, I didn't circle the 2 x's and the y in the first term, plus I didn't circle the 5 in that second term, minus I didn't circle the 2 2's and a 3, which if you multiply those together, that becomes 12. There's an extra x and there's 2 y's left over. So that would be technically your final answer. So let's get some practice going on so you can check out the practice and check your answers with the key out there. But in a few days, we're going to have a little factoring quiz that encompasses what we're going to be covering in the next couple days. So make sure you're keeping up on your work and don't hesitate to reach out for any help. Have a great rest of your day.